All right, let me just start this. We are going to talk about three different things: RIP, OSPF, and BGP. So the autonomous systems are networks which are under one organization control, right? And so between the autonomous systems, we have different protocols than inside the autonomous system. Within an AS, the protocol is different than between the AS. It is like this. Inside your home, you can share a lot more secrets than you will share with somebody outside your home, right? Similarly, inside your organization, your routers will have a lot more secrets than outside, a lot more information exchanged than with the outside routers. So that's why we have to have ASs. And AS is a very common term that we use throughout this AS, autonomous systems. Now inside an AS, we have many subnets, right? Each subnet is an Ethernet or something like that, and many routers. Some of these routers do not talk to the outsiders, some of them do. The ones that talk to outsiders are called exterior routers. The ones which are inside are called interior routers. So these are all interior routers. They are speaking interior routing protocol, and they are speaking exterior routing protocol. Okay? So few words here. Everybody is clear about what is interior, what is exterior, what is AS. Yeah.
The protocol is exterior and interior, or the routers itself?
Both.
So R5 is exterior router?
R5 is an exterior router and it speaks an exterior routing protocol.
Okay, but it also speaks with R8?
Yes, so it speaks with the interior also. All the exterior people speak to the interior.
Okay.
All the exterior people speak to the interior, so you cannot have some people who do not speak to the interior, they cannot give any information without interior. Alright, so interior routing protocol and exterior routing protocol. Interior routing protocol are also known as IGP, and the exterior routing protocols are also known as EGP. Interior gateway protocol or exterior gateway protocol. IGPs are two examples are RIP and OSPF. RIP and OSPF are spoken only inside the organization. EGP examples are EGP, BGP and IDRP. So there is a protocol whose name is also EGP and it is of the class EGP. So there is a confusion. EGP is both a class and an instance in that class. Okay? But IGP does not have, there is no protocol named IGP, so this is only a class and it has at least two members, RIP and OSPF. EGP has more members, actually all of them have more members actually. Even IGP has some more which we know, but I am not going to go through them. So here EGP has at least three, EGP, BGP, IDRP. Having done this, after this we will not really speak about any of those other two, we will just talk about BGP, which is the most common one. So BGP is the exterior protocol and RIP and OSPF are interior protocol. Out of those, RIP is the old one. So the only protocol, really two protocols that you need to know are OSPF and BGP. OSPF is spoken inside and BGP is spoken outside. So why RIP was? So RIP is the first protocol that was designed. Jan, you're really doing this class? Otherwise, close your laptop, please. RIP was the first protocol that was done, and it stands for Routing Information Protocol. It's a distance vector. Now, anybody remembers what is a link state and what is a distance vector? From this side, anybody knows distance vector? Just raise your hand if you know distance vector. Nobody knows distance vector and exam is next week? No, I know, but I just want to see from this side. Nobody knows distance vector and link state? Really? Anybody in the class? Not you, but I just want to see. I just want to see. If it is not getting through, how come? Yeah, go ahead.
Vector distances to all other nodes in the routing table.
So the distance vector and the link state. Link state was, we just tell the link state to the whole world. Right? And the distance vector is, now distance vector is where you tell what?
The whole world about your neighbor.
No, if you tell the whole world about your neighbors, then that is link state. If you tell about the whole world to your neighbors, that is distance vector, right? Yeah.
They don't know about topology structure of the network, and they transfer only routing tables, and the best of the network is the best of each router.
Right, so there are two algorithms, right? You are talking about some algorithm, right? So tell me which algorithm is which? Dijkstra's algorithm is which one of these two?
Distance.
Huh?
Distance vector.
Dijkstra is link state, and the other one was the distance vector, right? Bellman-Ford. And you got to read the book, man, fast. Because if you haven't read it this far, the chapter 3 we have come into, and I know many of you are not taking exam too, but if you don't read this, you will get hurt in the final exam, even though we are not going to ask about routing. But if you don't know about routing, then you won't be able to do the rest of this stuff. So the things build upon the top of each other. If your base is flaky, then you will not be making the final exam. Final exam is required. This exam is not required. So you cannot just say, all right, I will not study for this exam, so I have not studied chapter 3 or chapter 4. That's why I recommend that everybody take this exam. Even if you have gotten good grades in the first exam, and second exam is really not required, but it will be required indirectly in exam 3. You will have incomplete knowledge of networking. And distance vector and link state are very fundamental. I spent basically several times explaining that. So anyway, this is a distance vector. A vector of distances is of all nodes is sent to the neighbors. So basically the way I remember is that the big vectors are sent to my neighbors. Okay? And everybody, when they get the table, they look at their table and they create new entries. If anything changes in the table, they send it to their neighbors again. And we had a 3-node example before Bellman-Ford. This was distance vector. You send the whole table to your neighbors. And if it changes, you send it again until nothing changes. Okay? So this is all distance vector. So if entry is aged, remove the entries that have aged out. So basically, if the entry has not been used for a long time, then you age it out, and then you send the updates every 30 seconds. Now, the maximum network diameter is 15 hops, and the cost is measured in hops, and you find out the shortest hop path. May not be the fastest path. So you measure how many hops the distance is. In those days when it was designed, remember this is 1967 or 70s, they didn't have many different kinds of links. Everything was running at 56 kilobits. All the links were equally expensive, equally costly, and so on and so forth. And so the cost concept was not there, it was only hop concept was there. So you find the shortest route, which may not be the fastest route, and the tables are broadcast every 30 seconds. So there is a lot of bandwidth which is spent, and uses UDP with 576 byte datagrams, and therefore you need multiple datagrams to send the whole table. For example, a 300 entry table will need 12 datagrams. Now here is another interesting thing. If one person makes a mistake, then everybody gets that mistaken information, and then it causes a big problem. Okay, so let's see how the mistakes propagate. So this is called counting to infinity problem. I don't think this is in the book again, so please listen carefully. If something is in the book, maybe you can read it next day, but this one you have to really listen to it very carefully here, and this is important part of the problem. Is that, let's say R1 and R2 are exchanging some information, and the R1 says that I can reach A with cost 1, when one hop. Right? R1 can reach A in one hop. It sends it to R2. What does R2 note down? That to reach A, I can reach A in 2 hops via R1. So this is the table for A, table entry for A in R2. This is the table entry for A in R1. Now what happens is R1 loses A. Suppose this link gets cut off. Okay, between the first and the second announcement. So then R1 makes a note that the cost to reach A has gone to 16. 16 is infinity. Because the network cannot be more than 16, 15 hops. So the 16 is infinity. This is one reason why the network cannot be more than 15 hops, because if you have put number 16, that is infinity. It says I cannot reach R1. However, R2 tells it that, look, my cost to A is 2. So when it gets that message, that table, what does it make a note? That I can reach A via R2 at the cost of 3. Is that clear? Alright. And then it tells that to R2 that my table has changed. So R2 says, okay, I can reach A with the cost of 4 by R1. Yeah.
When are these being sent? Like, is R1 ever requesting that R2 send it the information, or is it just sent?
Now every 30 seconds, every time there is change in the table, every 30 seconds you send it to your neighbors.
So why wasn't the 16 sent to R2? Oh, so how did the 4?
Yeah, 16 was sent to R2, but he says I already know 2. I mean, like basically this one is overridden because I already have the cost 2, so then it is not noted. And this one says I have a cost 16. This one is noted because this is decreasing the cost. Increasing the cost is not noted. Yeah.
How come when R2 broadcasts, I can reach A in 2 hops via R1?
It doesn't say R1. See, here the thing though.
Okay.
Yeah, that's the thing is that this last column is not sent to the other side. It's only sent the cost table which says I can reach A with cost 2 and B with cost so on and so forth, right? So it doesn't say how. Yeah.
How would R1 lose the link to A? Like, when,
How when R1 use the link to A and lose the link to A? Lose. Oh, just disconnect. Somebody came and pulled the plug.
Okay.
As simple as that, yeah.
How do it changes in the R2 table from 4 hops? Do you understand?
Yeah, because see, thing is now this message comes here. It says my cost to A is 3. Now R1 says my cost to A is 3. It doesn't say that it is to R2. It says my cost to A is 3.
Okay, but it has cost to A which is 2. Why did he override it?
Right. Okay, let me correct myself. This message was never broadcast. This 16 was never broadcast. What happened was 1 was broadcasted as 2, then 16 it happened, but before it could do broadcast 16, it got a message from R2 saying that my cast is 2, so it changed that one, and then it sent that and it got changed here. So this 16 was never changed. Sorry, I said that 16 was higher, so it was not ignored. No. It was never changed because 16 was never broadcast. By the time the broadcast time came, first this message was received, so it became 3. So 3 became 4, 4 became 5, 5 became 6, 6 became 7, 8, 19. Finally, both of them say that the A is unreachable. And that took 16 intervals, like 8 minutes. All right? And it can be longer depending upon how many hops you're going around. But anyway, so this is called the bad news travels slow. Actually, bad news should travel fast. That's the good thing to do. Because if there is an attack or something, you want to know it beforehand, like an earthquake or something, right? You don't want it to travel slow. So good news can travel slow, but the bad news should travel fast. In this case, the bad news travels slow. So this is called the counting the infinity problem. Until you count from 1 through infinity, you can't figure out that this is unreachable. Now, is this example very clear to everybody? If not, please ask right now. All right, because of that, RIP is no longer used. Yeah.
I had a question. So the 4, why
Yeah.
does router 2 update from 2 to 4? Because it's an increase.
Yeah, 3 to 4, yeah. Yeah, right. So that's what I corrected myself, is that you can increase yourself. Yeah. So when it says that my cast to A is 2 by R1, and then R1 is saying my cast is 3, then it says, okay, so my cast is 4. All right. The main thing that was that the 16th message is not even sent because it happened in the middle and then it got overridden by 3. Yeah.
The book said something about a poison reverse for RIP.
Poison reverse.
Yeah.
It could be the same problem. It could be the same problem, but I think the poison simply means that some table is wrong rather than link going out. Here there is nothing wrong basically anyway.
So it essentially makes it so this sort of oscillation is possible between 2 routers. I think it's still possible with 3 or 4, but with a poison reverse, you can't. Yeah, hard to explain, but you can't go back.
So you keep oscillating between 2 numbers?
No, you can't. With 2 routers, with poison reverse, it'll go straight to the 16.
Both of them will go to 16? Okay, maybe it is the same problem then, I don't know. Could be the same problem. So I will look it up and then let you know if it is a different problem. But this is the main problem with RIP. So RIP is an old protocol. It might still be implemented in some older routers, but most of us today use OSPF. So that's another message. Even though we teach you about distance vector is old now, right? We use link state. So this is the one that we really need to know. OSPF, open shortest path first. And so several things, since it is the newer protocol, we use true matrix. So each hop is not the same. Every hop has a different cost, which is related to the speed actually. And it is a subnet mask, so it knows basically better than prefixes. And then allows load balancing across equal cost path. So if there are 2 paths which have the same cost, you can use both for load balancing. There is a little bit of detail there which we are skipping here, but it is not that you just send 1 packet here, 1 packet there, because if you do that, everything will arrive out of order. So generally you send 1 flow here and 1 flow there kind of thing. So load balancing across equal cost path. It supports type of service. What is type of service? So if you remember the Ethernet packet format, there were 4 bits which says type of service. Those bits have been there since the beginning of the IP protocol, have not been consistently used by people as to how to do it, but they are supported in OSPF. In whatever way you want to use, it will calculate 16 paths, because 4 bits means 16 different possibilities. So you could just say, for this is the cost, for this type of service this is the cost, for this type of service this is the cost. It can create 16 tables for 16 types of service. Allows external routes. Route learns from the other autonomous systems. So if an exterior router says that I have a path and here's the cost, OSPF can learn that one as well. Authenticates route exchanges. So everything is authenticated. So when you learn about network security, there we teach how to send a message that is signed or at least protected, so that if somebody made a 1-bit change or if an error happens, we already know CRC detects the error, but authentication means that we are guaranteeing that this message is sent by me and not by somebody else. Somebody else cannot send a valid message. With CRC, anybody can send a valid CRC message, but we will figure it out with authentication. We will figure out that it did not come from that router, right? So it is like signed message. Authenticates route exchange. Quick convergence. Converges fast, unlike infinity. Direct support of the multicast. So it can also handle multicast, which means that you really need to find out the path for multicast tree. And link state routing. That means each router broadcasts its connectivity with the neighbors to the entire network. So here's the thing. I tell about my neighbors to the whole network. So every message I send is what we call flooded to the whole network. And therefore your network cannot be very big. Right? If a network has 1 million nodes, 1 million routers, you would be just flooding and doing nothing else. What million? If you have 1,000, it will be too big. So you keep small numbers, and therefore you divide your network into areas. This is one area, this is another area, this is another area, this is another area, area 1, 2, 3, 4, and then there is a backbone area, and there is an external area. Anyway, so basically each area runs its own OSPF. Yeah.
Could you explain again the types of service, supports service?
Types of service. IP packets have 4 bits which are called types of service. In the beginning, it was envisioned that we will put there some code for time-sensitive protocols or something which is, throughput sensitive or something like that. Different kinds of service we will provide to different IP packets, although it was never consistently used. Some people use it for priority, saying that we could have 16 priorities out of those 4 bits, but it has not been consistently used.
Okay, and quick convergence?
Yeah, quick convergence means it doesn't count to infinity. So the bad news travels fast. Yeah.
You said that it was an IRP, but so then how can it support external routes?
Oh yes. So the question is, I said that this is IGP, this is Interior Gateway Protocol. How does it support external routes? It just learns, that's it basically, that's all it is. So it knows that if a packet is going to that place, you should send it to me. If it is going outside, then we know that we can figure out the path from here to there outside. So this one actually is designed along with BGP or after BGP, so they understand that there are outside routers as well. It doesn't really speak BGP. It doesn't really, so some router will speak BGP and OSPF. That will understand from BGP. It will learn some external destinations, and it can tell other routers. So OSPF can send a message which says, well, here is the cost to this node, through some other protocols or something. Yeah. Any other question? All right. So we are back into the areas. OSPF requires you to divide your network into areas. Even though it is all one AS, one autonomous system, one company, one organization, but if the organization is big like WashU, it will have many areas. If I can think about it, I would really not be surprised if there are at least two areas, medical school and this school, right? So each area has 3 routers. Each area has a designated router, a backup designated router, and all other routers. So there may be more than one router, more than 3 routers, actually maybe 15 routers in area. But there is one router which is designated to get out of the area. That is the exit from the area. Anytime you want to get out of the area, you send your packets to designated router. It's like your default gateway. Okay? And then a backup is kept. In case this goes down, the backup can come up, so it keeps all the information current. And then everybody else is internal router. So they are not designated, they may not have the path up to date and all that. So each area has 2 routers, designated and the backup, right? And then everybody else. Similarly, the backbone has a backbone router. There are many backbone routers, and then they have what they call area border routers. This is like designated. This is like getting out, well, area border router. So this is getting out to other areas, and then AS boundary router, which is that getting out of the AS itself. AS and area. AS is the autonomous system, and so when you're getting out of the autonomous system, there is a boundary router there, and there is a border router here for area. Yeah.
The boundary router is an exterior router?
Exterior router, yeah. So from area you go to the backbone, from backbone you get out. Or from backbone you go to some other area. So when you want to go from area 1 to area 4, you will, or let me do the example other way around. When you want to go from area 4 to area 1, you will go to your designated router. From there it will send it to some backbone router. From there it will send to the area border router. From there it will go to the other area. And backwards. So everybody understand the function of the designated router, right? Everybody understand that? All right. So designated router is a default gateway. Yeah, question?
Yeah, I just don't get the difference between designated to area border.
Okay. Area border router is only in the backbone, and there are many of them because each area border router will connect to one or more areas. Designated router is in each area, and it has basically it is the default exit from that area, and it will be connected to a area border router on the other side. Yeah.
In this picture, why is it nothing better connected to an area border?
This one?
Yeah.
Yeah, this should be labeled as area border router. These are all backbone routers. Backbone routers could be any number, just like internal routers. There could be many routers in the backbone. They are internal to backbone, but this is a border router. Yeah.
This is called like the backbone area, and that connects all the other areas?
Yes. So they just have a 2-level hierarchy. You have lots of areas. They are all connected to one central place. Yeah.
Could you potentially have more layers if you get a really large network?
Tree, yeah, right. So the question is, can we have more tree layer? No, actually. So they just decided to have 2-level tree, and the largeness comes in the width of the tree rather than depth of the tree.
Wouldn't that be then run into the problem that you had if everybody is just using this structure, then you're flooding the network if it gets too large?
Okay, so you're not flooding. The thing is, yeah, what you're doing is, flooding is only inside an area. So this information is not flooded outside. This is flooding inside the area. Then somehow this designated router compresses that information and says that any packet going to this area have to come to me. So here what the flooding is being done is basically a big prefixes. You see what I mean? So the information here is everywhere is basically to the size of the area. So as long as the area size, flooding is inside an area, that's the point. So the flooding does not go from one area to the next. Does that answer your question? It would be nice to hear things. I mean, there is one way. I mean, you could bring the tree so that it is balanced both in width and height, and have a nice binary kind of tree. However, I mean, then basically you need a lot more of this hierarchy and makes it more complicated. So to keep life simple, they just decided to do a two-level tree where everything goes to the backbone, and then life is simpler that way. So it is simplified, and again, if you, I mean, generally the organizations have found that this is sufficient right now, and if the organizations become much bigger, generally what happens is they don't grow in the same location. They grow somewhere else, then it's totally different AS. Right? In one location, only so much you can grow. If suppose WashU has a Saudi Arabian campus, then it will be a different AS. All right. So now we know lots of words. We know internal router, area border router, backbone router, AS boundary router, designated router, and backup designated router. We have introduced all of those. If you have any question about any of these names, ask me now. Matrix. Sorry, yeah.
So the autonomous system boundary router, is that just another word for external router?
That's autonomous system boundary router is another word for external router, yes. Actually, external router is not used that much. This is more used. So, matrix. So the metric which you saw in your routing table in your computer when you did route something, that metric is inverse of the speed of the link. You take the speed, divide it into basically 10⁸ by the speed, the number that you get is the cost of that link. Slow speed links cost more, high speed links cost less. So it is not really the dollar cost, it's the throughput basically value. So we want to use least cost, means we want to use high speed links. Obviously, I mean, this is not, it doesn't look like something reasonable, but when the speeds were more in this area, 1.5 or 64 kilobits, then these numbers were meaningful. Now we have 10 gigabit network. If you divide by 10⁸ by 10 gigabit, you get 0.01 and very small cost. And then the question is 10 gigabit and 1 gigabit, are they properly costed here? I don't think so, but basically this was a simplification again, that they assumed that the cost of the link would be inversely proportional to the speed, and this is how it is automatically calculated. However, I mean, you can change the cost. So if you wanted to put some number for 10 gigabit and some number for 1 gigabit and some number, you could use those numbers. But this is how it is calculated. Okay. So, yeah, go ahead.
Why does the slow speed link cost more again?
A slow speed link, oh, because they are not good to use. That's all. Yes, we are not calculating the dollar cost here. We are calculating the path which is the best path. Remember, the purpose of OSPF is not to minimize your dollar amount. Purpose of OSPF is to maximize your throughput. Right? You understand that? Right? So we are just trying to find out, when we say least cost path, we mean that the fastest path or the best path. It's like this. Highways probably cost more money than the street roads in the city. But we take highways when you want to go somewhere because they are the fastest path. Alright, so now I understand the metric. So the maintaining the database is continuously checked for synchronization by flooding LSAs. So I have used the word flooding and I use the word LSA. LSA is link state, what? No, it's not algorithm. Link state, I was going to say vector, something to do with the vector, and I am missing the word, not remembering the word.
Say algorithm.
Advertisement.
Something. Let's just leave it alone right now. So you just send the link state vectors, link state whatever LSAs. That is basically your advertisement. Link state advertisement could be. So link state advertisement. So you flood those, and all flooded LSAs are added. So this is how it works. I send my LSA to these 8 people here. I will get 8 acknowledgements. Each of them will send it to 5 or 8 people. They will get 5 or 8 acknowledgements. If suppose you send to 8 and you get 7 acknowledgement, then whoever didn't acknowledge gets it again. All right. So all flooded LSAs are added. Unadded LSAs are flooded again. Database information is checked. If new information, it is forwarded to other adjacencies using LSAs again. When an entry is aged out, the information is flooded. So when I aged out, when I remove something, then I tell them other people too. So Dijkstra algorithm is run on every new information to build the routing table. Okay, that's why you see the importance of Dijkstra's algorithm.
It's link state
Yeah.
acknowledgement.
Huh?
It's link state acknowledgement.
Link state acknowledgement? Well, that doesn't sound right to me.
Yeah.
Huh?
I just looked it up. It says link state advertisement.
Advertisements, yeah. Advertisement makes sense. Okay, you have a question?
Yes. What database are we talking about?
Oh, this is the link state database. This is basically the table, routing table. All right, that's all about OSPF. Any question about OSPF before we go to BGP?
Just one more question.
Huh.
How is an entity aging up in this database?
If it has not been updated, so thing is, when you update an entry, you write down the time, you say I modified this entry that the best route to Kansas City is Route 70 West. I wrote it down today. And then no new information came in, it was not changed, then we say, well, we are going to age it out, as if it was not used. But I can really not imagine as to how it will really not be updated. I mean, I would think that some new message will come from the neighbors and it will say that it has been updated, so it has been refreshed again. Once it is refreshed again, the new time is written down that I calculated this at this time. If something is not updated, then it is aged out.
So it's based on some time value?
So every entry has a time, yeah, time when it was written or calculated. All right, so that is OSPF. Now we come to BGP, Border Gateway Protocol. So this is inter-AS protocol. It goes between the ASs, and it has been used, now it is used very extensively. 1989 it was started. It runs on TCP, segmentation and reliable transmission, advertises all transit AS on the path to a destination address. So this is unique. It doesn't simply tell you that my cost is so much. It says that if you want to go to Germany, you can go through me, I will send you to New York, from New York you will take a flight to Frankfurt, from Frankfurt you will take a flight to that. So the whole path is included in the message. So it is not a number, it's a path vector. And for every AS, I can tell you what is my path vector. So it's a big database. Because for everyone, like remember in the previous one you said, how come I don't remember that, this cast 2 is R1, right? Because they don't remember the path, right? And they don't tell the path. But in BGP, we tell you the whole path. And so the database is quite big, and the information that is exchanged, the path vectors are very large. And a router may receive multiple paths to a destination, so we can select the best path, because the best path is not selected by caste. There is no such method that I want the fastest speed. It depends upon where the path goes through. If a path goes through AT&T and Verizon and you got AT&T service, you are not going to take a path that goes through Verizon. Right? So all the paths are not equal. Some paths are totally blocked. Some paths are good by my policy. Some paths, if it goes through Russia, maybe it is not good for US government traffic to go through that country. Right? So the idea is it is policy based. It is not caste based. Caste is not the criteria. Criteria is what is my policy, what is my agreement, what is my business partnership. Alright? So BGP uses path vector. This much you should know very well, anytime. That it is not you just have a link state and things like that. You give the whole path, and you may have multiple paths, and then you select the best path yourself. And the best has to be defined by yourself. Nobody can tell you what is the best path for you. You get a path vector from your neighbors or from whoever, and then you compare them and decide that my path to go to Germany is this best path for me. For example, the simple example is St. Louis guys probably will go to New York or Chicago, and San Francisco people will go for Germany, some other place, some other flights. So everybody has a different path, and they select the best path depending upon their own criteria.
What information is in the database? Like
path. So basically it says to go from this AS, I have to go to that AS, to that AS, to that AS.
Okay, so it's for each router where they can go to. And then
This is a list of ASS.
So it's like I have all the ASS and
Yeah, for each AS we will have, so for my next AS I will have the router address.
calculate all the paths.
So I will just send it to the next AS, and they will calculate for the next AS, but I know the path beforehand.
How do you know the path?
How do you know the path?
Yeah.
Oh, you just exchange these path vectors. The BGP routers exchange the path vectors.
Or you trust the router to give you the right vectors?
And?
You trust the other router to give you the correct vector?
Oh yeah.
You have to,
Right, so the question is, do you trust the other router to, so the thing is, if I connected, so let's say Vashu is connected to 4 other ASS, maybe it is connected to AT&T and Verizon and Sprint. So we trust these 2, right? We trust these 3. And there is an authentication, of course there is an authentication so that nobody else can pose to be in Sprint. Right, so there is an authentication beforehand. And now it is quite possible that the Sprint has gotten wrong information by some mistake. So yes, that possibility exists. Right? But generally it is okay. Alright. So let's see what else is left. A router may receive multiple paths, can choose the best path. IGB, so there are two variations of BGP, IBGP and EBGP. I is used inside and E is used outside. So you need whatever BGP information you get, you have to tell all the boundary routers and backbone routers inside your network that look, if you want to go to Germany, this is the way. Right? That is used, so there is a protocol for that, and it's called IBGP. IBGP is not a calculation protocol, it is simply informing everybody that this is the way to the outside world. Right? EBGP is the one that is used to exchange the information, calculate the best route, and so on and so forth. So EBGP is the protocol designed to talk to the outsiders IBGP is the protocol designed to talk to the insiders. So everybody can see the difference between IBGP and OSPF. Right? OSPF is used to calculate the path inside the routers. IBGP is simply used to announce the path to inside routers, how to get out of this whole AS. All right? And so initially they will exchange entire routing tables, afterwards only updates are exchanged, and BGP messages have the information as to how they found the information by RIP or OSPF or by BGP and so on and so forth. AS path, so this is the list of all the ASs on the path to reach the destination, and the next hop, IP address of the router to the next hop, and unreachable if becomes unreachable. So now this answers your question as to what is in this vectors. Basically it is the list of ASs. For the next AS only we will have the IP address. For the other ASs we just have the ASS name. Each AS it has a number which is actually used, AS number. Now BGP speakers, now this is a term we use. BGP speakers generate update messages to all peers when it selects a new route or some route becomes unreachable. So BGP speakers means any router that speaks BGP or that follows BGP, it will send a message whenever routing table changes.
So define IBGP or
eBGP we are talking about. See, well, yes, ma'am. So generally eBGP is the one that is sent out, to all the neighbors and all that, and then they calculate their own paths. So that is what we are talking about here. Now if something came from outside and that said that now the path for Germany is not here, you have to go to San Francisco from St. Louis, then we have to tell the neighbors, and we have to tell internally. So IBGP will simply announce that news. Yes. So I think if your question was the change of table is sent to both internally and externally, answer is yes. If your table changes, you will tell the internal people also that the New York airport is closed today because of the snowstorm or something, and so you can't use that airport. All right, now it is policy. Why it is policy is because you are careful, because everybody has to pay everybody else for the traffic. So here is an example which is actually from the book. The book, so basically there are three what we call the companies or customers, W, X and Y. X, Y and W are the customers, A, B, C are the ISPs. X is dual ported to B and C, Y connected to C, and W is connected to A. So A, B, C are provider networks, X, W, Y are the customer networks, and so actually these are called stub AS, stub, S-T-U-B, stub AS, and so they don't do any routing for other people, they just do it for themselves. So no traffic would be coming here and going from C to B, not by X. X doesn't provide any transit service. They are stub networks. So everybody who wants to come to X comes to X, and then basically not as a. So this is like only residents allowed kind of a street. Anyway, so X is dual homed, attached to two networks. X does not want to route packet from B to C. So it doesn't like somebody comes from B and goes to C. So X will not advertise B to be a route to C. So when it tells what are the places you can reach, it will simply tell, X will simply say that you can reach my nodes through me, period, that's it. And similarly it will tell C that you can reach my nodes through me. It will not, even though it will get from B the whole world's map, and from C it will get the whole world's map, but it is not going to advertise that to anybody else. All right. Now let's look at AW. So A will advertise path AW to B, and B advertises the path BAW to X, and should B advertise the path BAW to C. So should it tell the C that if you want to go to W, then you can go through me? It depends. It depends upon whether there is a dollar amount there or not. So the answer here is no, because B gets no revenue for routing CBA traffic, since neither W nor C are B's customers. Right? So it will not tell C that W is accessible through me. So there is, you see the difference between OSPF and all this. Here it is all done by the marketing, by the people who really deal with real money. And depending upon whether there is money or not, they will decide whether to advertise the path. So B wants to force C to route by A. So it says, well, if you want to go to W, go by A, and so B only tells about its customers, which in this case is X as shown here, and so it will take from C only traffic that is going to X, and so on. So this is policy-oriented routing, not cost-oriented routing. Cost-oriented, actually, it is cost-oriented if you want to call it dollar cost. But basically it is policy-oriented, so you decide and how you want to, who you want to let go through your network. So inter versus, so the difference between intra-AS and inter-AS should be clear now. Intra-AS, we don't worry about policies too much. Everybody can go through any router. Right? But inter-AS, it's all policy. So inter-AS, administration wants complete control over how its traffic is routed and whose traffic goes to its net. So intra-AS, single administration, so no policy decisions. Scale, hierarchical routing, table size, reduced update traffic. So because we can make a tree, here the tree doesn't help. BGP, right now the big problem that we are discussing in IETF is BGP is unscalable. It is becoming out of its scale. Basically the tables are so big, there is so much traffic, and it is going worse and worse. So one of the problems that people who are working on next generation internet are working on is how to reduce this BGP stuff. Anyway, so inter-AS is policy, intra-AS is performance. So everybody is clear, understand the difference between BGP and OSPF criteria. OSPF is a mathematical algorithm, you just run Dijkstra and you are done. BGP, there is no mathematical algorithm. You write down lots of ifs and buts, ifs and then, if and then, if then, and if then, and every company has their own list of if then table. Okay? Yeah.
So it says that the intra-AS, could you explain again the intra-AS without the policy?
Yeah, intra-AS, here, intra-AS focuses on performance. Intra means inside the AS. Inter-AS, between the AS, we focus on the policy.
Oh, so the intra-AS is more like
OSPF. Intra means internal.
because the intra-AS is a BGP?
OSPF.
Oh, okay.
Intra-AS is OSPF. Inter-AS is BGP. Alright, if it is all clear, then we finish the three protocols. RIP. Now RIP uses distance vector routing, and so it had this problem of counting to infinity. RIP version 2 has fixed that problem, and there were 2 or 3 solutions which I did not go into that because this is anyway out of date. OSPF is the latest basically protocol, link state routing protocol, and it divides the autonomous systems into multiple areas, and therefore you have area border router, AS boundary router, and for whatever reason they use the word border here and the boundary there. I don't know the difference, but basically, for the AS boundary, for area it is border. And then there is a designated router. Everybody knows what is a designated router. That's the exit, basically designated exit, because there are many routers, so you want to go to the designated router. And BGP is an inter-AS protocol, and therefore it is driven, policy driven. So I did not cover check section 4.7. I think 4.7 is multicast. So we did not cover multicast, but we just covered the unicast here. And so you should be able to do these problems, and you should read section 4.6. Any question? If not, then let's just summarize the whole chapter before we move on to the next chapter. And so in this chapter we had many things. The first thing we did was we talked about forwarding. In fact, we talked about how the routing forwarding works, and we talked about IP and IPv6. And IPv6 uses 128-bit addressing, whereas IPv4 uses 32-bit addressing and all that. And then we went into the routing algorithms. We talked about Dijkstra's and Bellman-Ford's, and then today we talked about the protocols, RIP, OSPF, and BGP. RIP and OSPF are both IGPs, interior gateway protocols. OSPF is the latest one, that's what we are using. It's link state, and it's good. Distance vector is outdated. And then BGP is an external gateway protocol, and it uses path vectors. So you need to know the whole path as to how you get there, and not just the next hop. Okay, that's the end of this chapter. Any question? By the way, I did give you this slide on link local addresses, so that will be in the exam as well. All right, any question?